but reformed. But he, when he first came to my lab, the first project he worked on was to try to understand something about the olfactory system of insects, they call it the antennal lobe, which is a very dynamical little nucleus in insect brains, which processes, gets input from the olfactory receptors, and in fact, the model produced beautiful oscillations, which are observed. This is work that was done with Gilles Laurent's lab at the Caltech. So we had the data, we had the, and these were classic papers now because they really were the first time that Hopkins-Huxley kinetic models were developed that could reproduce a lot of the observed activity and the mechanisms now that we could understand how that then created not just the oscillations, but adaptation and a lot of other observed phenomena. So he's gone on from there to the cortex, and you'll be hearing about that. He's now in the Department of Medicine here at UCSD.
Yeah, primary critical care sleep division, which kind of probably sounds strange. Yeah, I was mentioning about collaboration with Igor. I remember I came to Canada, it was January, very cold. And I started writing some equations, and Igor saying, what are those? So what we're gonna do? So anyway. Yeah, so I'm going to talk about sleep and memory. So it's very much related to Eric's and Yuri's talks this morning. So to start with, this is a slide I usually show. There is a huge literature kind of supporting ideas that sleep play an important role in memory consolidation. But for me, possibly one of the most kind of maybe indirect but important evidence is that the sleep structure, how stereotyped, how preserved sleep structure across animals. So this is a kind of typical human hypnogram which shows transition between lots of slow wave sleep, early in sleep, and REM sleep later. And this is recordings from fly which shows it can be called really REM sleep and slow wave sleep, but there is a deep and paradoxical type sleep in those animals, and it's also play a role in memory, can train those kind of creatures to do something and then put them to sleep, to distract. So it shows very similar patterns to what we see in high animals. So what sleep does to memory, typically we talk about consolidation, kind of process of moving memory from short to long-term storage, and I'm going to talk about this a lot, but essentially there are lots of things I believe sleep do in respect to memories. So it's, again, it's transforming recent memories to long-term representation, it's reducing interference, also including what we like to call reconsolidation, changing the representations of the old memories as we learn new things. It's sort of generalizing episodic memories, transfer of knowledge, forming some relationship memory, and so on and so on. So I'm mainly going to talk about sort of how we believe sleep can prevent interference when we learn new things. And just a couple slides. I'm not going to talk much about sort of AI-related work we did, but as some of you definitely know, that continual learning, it's kind of unsolved problem in AI. You can take beautiful LLM, which is like ChatGPT-4, whatever, and you can fine-tune it. It would do better. But if you seriously train it on new data, you will start losing all information. So this is plot from a very nice paper by Andreas Tolles, who is not here today, but he will talk virtually on the afternoon. And it shows if you train a very simple kind of data set, is broken into several tasks, then essentially performance on the whole data set drops down to, like, we learn first task, it's 100% on that task, but eventually getting 20% because between 5 tasks, everything is called 8 and 9. So essentially everything what was shown before largely forgotten. And there are some approaches, some more kind of brain-inspired, some less, to prevent it, including kind of using old data, which combined with new data to train, or kind of trying to figure out what weights may or may not be changed. A couple of years ago, we proposed an approach kind of inspired by sleep, when we essentially can train artificial neural network like usual way using backprop. We can implement something like sleep phase later on, which would have some Hebbian plasticity, synaptic weights would be changed. We can bring it back to artificial neural network state, and we can recover a lot of performance. This is sort of example. There are 5 tasks, and let's say after training task 2, remember, model only knows task 2, 95% performance, everything else is not, so it's called everything, whatever is task 2, like 6 or 7. But then you have a sleep phase which is totally unsupervised, and you recover lots of performance. And at the end, you can get decent recovery, kind of around 70s, even higher what we're getting now. Okay, again, I'm not going to talk about back to neuroscience. So one very influential idea about how brain deal with problem of catastrophic forgetting and enabling continual learning is it has different versions of it. It's called complementary learning system theory or dual memory, but essentially it's what have been already discussed quite a bit today. It's a learning strategy when 2 distinct systems are involved. One is hippocampal system, which learns fast and presumably forms some kind of sparse non-overlapping representations. And then during offline periods, such as non-REM sleep, interaction between those 2 systems allows kind of nicely and carefully embed memory traces from hippocampal network to neocortical network. So again, it's kind of nice way to move forming new memories away from like awake state when which potentially we can easily overwrite all the memories to the long offline period of sleep when interaction between those 2 systems and different rhythms which have been mentioned, ripples, slow waves, can create sort of nice environment to form those representations. Long-term memories without forgetting old one. But I like to argue that in principle that system itself, that model itself does not immediately kind of solve a problem, because essentially this is a cartoon. I tried yesterday to use ChatGPT to generate something nice, and after 30 minutes I gave up. It was totally horrible what was produced. But essential idea, if you have a bunch of neurons and let's say this is your memory, like sequence 1, 2, 3, 4, and activating that sequence means mouse find a way to piece of cheese in maze or whatever. And then, let's say, hippocampus learns new pattern, and then it starts kind of carefully teaching cortex. So it's pushed that, so ripple representing new pattern, 1, 2, 3, 4, now projected to the cortical network. If nothing else happens, it can easily override that memory. So it can create new pattern, but the old one can be gone. So in a sense, kind of moving from awake learning to this hippocampal cortical interaction during sleep, not solving the problem. It's, in a sense, pushing it to slightly different domain, but the problem still remains. If all the memories are not reactivated, as I'm going to argue a bit later what is maybe happening to protect it, then new memory can take over. And essentially, we go from that situation to that one. So the question is, how does that hippocampal cortical network can organize reactivation of all the new memories to avoid interference? This is essentially what we wanted to ask. And I will talk about 2 kind of type of data. One is modeling, and this is a type of model. So very briefly, it's a biophysical model, but it's pretty simple. It's layer of pyramidal cell, inhibitory interneurons. And it's actually good that it's simple, because reviewers very commonly criticize us, saying that model is too complex, and because of that, it's too specific, and so on and so on. It has thalamus, which not playing a significant role here. It has a kind of random connectivity matrix within certain radius, and a network capable of transition from wake to, I'm going to talk mostly from wake to slow wave sleep, but in principle we can simulate other sleep stages by changing, by simulating effects of neuromodulators. We are not explicitly modeling like LC or some other areas, but we can model what release of acetylcholine or epinephrine can do to neural circuits. And I will more briefly, but I will talk, this is collaborative work with Bruce McNaughton lab at UCI. And what they did, they have a mouse train on this virtual environment, and they train it to two different environment. One could be called familiar, and one is novel, and they could look at reactivation, and I will show you that some, these recordings actually very nicely confirm model, and in fact what we learned from model, on the other hand, from some things let us go back to model and figure out something new. Now, next two slides is something we published a few years ago. There is no hippocampus in this, again, next few slides, but I would like to show it because it also illustrates what we are doing. So again, this is a same network. It can do slow wave activity as well as wake. So our memory patterns are very simple. I'd like to argue that on one hand, everything we learn is probably sequences. So in a sense, whatever memory can be represented by patterns of neuronal groups activating in a certain order. And this is a super simple sequence, like let's say our memory 1 is activating those groups in that particular order, EDCBA. And we can train it in the wake. We can get some improvement. This is performance we can test by activating first letter and see how it's completed. So we train it in the wake, we get some improvement. We showed before that if we have slow wave sleep, we have actually then huge bump in performance, and this is a classical case of reactivation. We showed that that sequence will be spontaneously reactivated during up states. Model has plasticity, and it will change synapses, and performance will become higher. But then what happens if you train opposite sequence, which involves the same group of neurons activated in different order? This is probably the most extreme case of interference. And we consider it also less overlapping memory traces, and we found similar results. But again, this is the case when our second sequence really trying to take over synapses trained by first one. And you can see interference. So this is performance of the first sequence after we train second one, and we go from here to here. And second sequence obviously improves. What we found, what we showed, that if we implement sleep phase later, it's actually improve both memories. So somehow sleep not only able to, essentially again, it does both. So it's improved performance of old memory, and it helps to boost up more performance higher for the new memory. So this is actually what we would like to do. But of course, there is a problem here. So if you train that second memory for too long, we can erase original memory to the extent which it would be not recoverable by sleep. And if you train second memory too little, then we never get to the point when sleep can actually pick up on that and consolidate it. So that's kind of, again, model system, which I believe more related to how we learn procedural memories, like skills and so on, but not how we quickly learn declarative memories. So one conclusion from that paper, it was last slide there, was showing that that point I mentioned earlier. We usually talk about memory involving, sleep involving consolidation of memory. So we take like recent trace and make it better, stronger, embed to the long-term storage. What we would like to claim is that, in fact, sleep does more important thing. It's not only does that, but it's also changed the presentation of the old memories as we learn new stuff. So those representation of the memories are always dynamic. So, for example, when this whole population of neurons was available for memory 1, they all synapses can be involved in recall that memory and so on. If we train opposite memory and let sleep to deal with that, we end up with kind of state when some part of resources is allocated to the new memory and as expense of old memory, but it's still capable to maintain those both memories within the same population of neurons. Now, very briefly, this is another project which should be published or submitted at least a year ago, but it's still work in progress. But you saw already, we like to talk about manifolds and attractors, and usually from experimental perspective, you can do it only looking at activities of neurons, because we don't have access to synaptic weights. So in the model, we have access to all synaptic weights, so we can actually see what happens when we train memory or have a sleep in synaptic weight space. And essentially, this plot summarizes everything I showed you before. So if we start from naive state and we train some memory, we are getting to the state when performance of that memory improved. And if you let sleep to go, it's pushed to some more extreme, possibly, state, which we call attractor for that memory, which is really stable attractor. So if we now try to, for example, if from that point we start train S1, we first train S2, we got here, if we continue sleep, we end up being here. If we instead of start training S1, kind of overwriting S2, and then implement sleep, it depends how long we train it. For those trajectories, you see we let sleep go, and it's push it back to the same attractor state. But if you cross some boundary, then subsequent sleep start to move system to the new attractor state when both memories are happy. And what we are not showing here, if we overtrain S1, we can end up somewhere here, and sleep will push it to the state when only S1 memory survives. So this is the idea, I don't have time to talk about it, about sort of each memory representation is not unique in weight space. There are multiple states which maintain each memory, and sort of overlap between those is probably where we want to be to maintain performance on multiple tasks. Okay, but now I'm going to move to actually what is more recent work, which we are trying to now put together as a paper with Bruce Lab. And I'm going to talk about, well, this is an example of slow oscillation, I already showed them, and this is an example of ripples, which I don't need to show because it has been shown a lot today. But essentially, like I mentioned earlier, if we train second memory in awake and allow a hope and then sleep can fix the problem, it can do it, but then we should be careful how long we train second memory. We don't want to overtrain it or undertrain it. So the question we ask, what if we, instead of training second memory in awake, we try to embed it using this kind of complementary systems, this dual memory kind of framework. So what we do here, we train first memory in awake, and this is again EDCBA sequence. And instead of training, we can implement sleep after that, it gets better, but in this case, we then start to train, again, very conflicting memory, A, B, C, D, E, but we train it in a way we think hippocampus talk to cortex. So this is, I should emphasize, this is an open loop model, so it doesn't have hippocampus. We have other model when we actually look at interaction, but in this case, we do very simple thing. We're saying, okay, this is a pattern delivered by ripple, and we can deliver it at different times during slow waves, and we can see what happens. So in fact, what we did, we delivered those ripples at 3 different conditions, like when delivered during near to down to up transition of slow waves, in the middle of up state, and near up to down transition. And I should say that actually we initially look at those 2 cases, largely driven by kind of results like that. This is from Yuri's lab and shows lots of ripples happening with some delay near down to up transition. But then when we got something and start looking at experimental data, it suggested this interesting situation going on here. And we go back to the model, and it turned out to be also working well. And then we saw this bioarchive paper, now maybe in press, from Buzaki's lab, which you already showed briefly, which basically shows that lots of ripples happens both near up to down transition and with small delay near down to up transition. So essentially, these are both very interesting cases. But let me go back to the model. So again, we have two memories. One is kind of, this is baseline performance. We can train it in the wake. It has a high performance, and then we can look what happens if we follow with sleep. The second memory have been never trained in the wake. This is baseline performance. This is after, this is both awake states. This is after red memory was trained, so blue memory was damaged by definition. And what we found that if we deliver ripples near down to up state, we actually do basically what we want to do. On one hand, we allow system cortical network to learn second memory, so performance shows increase from whatever, from 0 to what we usually consider very good performance, without any cost to the old memory. In fact, old memory in this case improved performance. So okay, it sounds great. So essentially, we can do successful consolidation, and both new memory and old memory doing well. Then we look what happens if we deliver ripple in the middle of upstate. And it turned out that in this case, new memory is not learned at all. So this is red one again, performance for the old memory. So old memory was successfully improving performance, but the new memory, blue one, shows slight, maybe slightly significant increase, but basically it's still below baseline. And finally, we look what happens if we deliver ripples near up to down transition. And we found case kind of like first one. So we have a very significant increase for the new memory. So it's trainable. So it's totally different from when we do this middle upstate kind of indexing. And red old memory still improve its performance. So essentially, again, we have a kind of best of two worlds. So we wanted to look next what actually happens, why it works for kind of down to up, up down transition, and it doesn't work for new memory for mid upstate. So essentially what we did, let's say we deliver ripple in the beginning of upstate. So we can define kind of indexed phase, which would be, I think, around 80 or 100 milliseconds from the beginning of upstate. And the rest of the upstate we'll call not indexed phased. And we can, or in this case, indexed phase will be in the middle, yeah, in around when ripple was delivered, and beginning or end of upstate is not indexed phased. And for each of these phases, we can also look on reactivation of each memory. Again, this is a model, so we can have access to all the spikes, and what we can do, we can see how much each synapse is reactivated in direction of given memory. So what is shown here is basically synaptic connectivity matrix in the region of interest where we have those 5 groups of neurons. And each dot here is a synapse. And because remember, we have one-dimensional network, so all synapses goes from high indices to low indices would be representing memory as 1, so they're kind of sitting here. And all synapses supporting new memory goes from low to high indices, so they would be sitting here. And finally, color of this shows how many times over all upstates we have net LTP effect on that synapse. So for example, if we have a red dot, it means that almost always it was showing LTP. And in fact, we have total about 450 upstates. So what is shown here, every dot here is when we have net LTP event on that synapse in over all upstates. And if it's below that threshold, we're just not showing them. Okay, it was long description, but we can see here, if you do down to up indexing, so this is a new memory, and you see during indexed phase, we have all the dots here, so new memory is happily reactivated. So we apply this kind of hippocampal-like indexing, and beginning of upstates reactivates that new memory. That's why it's performance improving eventually. But with the rest of upstate, we see that network reactivates actually old memory, which is kind of nice, which this is what we want to have. We want to have some sort of interleaved, well, that's kind of long-standing idea how to avoid catastrophic forgetting, to interleave all the new memory traces also used in machine learning. But here we're getting it for free. We are getting it, again, we index here, we're getting reactivation. The rest of upstate reactivates the second memory. If you look to the mid-upstate indexing, Again, not index-phased, still reactivate old memory. In fact, it's always reactivate old memory. And index-phased largely still reactivate old memory. We have some initial reactivation of the new memory, but never propagate through entire network. So it kind of fails. So this ripple cannot trigger full reactivation. It's in fact still largely what network is doing is reactivating old memory. And finally, if you go to down to up, we have a situation similar to the first one. Again, not index-phased reactivate old memory, and index-phased reactivate new one. So if you sum up all this as a sort of histogram, this is what we are getting. So not index-phased of the ripple, whatever it is, beginning, end, or middle, would always reactivate old memory trace. And the indexed phase, in case if we index near down to up or up to down transition, it's reactivate a lot new memory. If ripple arrive in the middle of upstate, it's basically we have some reactivation of new memory, but it's much less than in other two cases when we still have larger reactivation of the old red memory. I just wanted to mention briefly, it was some discussion earlier today about if ripple can trigger upstate or not. And this is actually some simulation from closed loop model. It's a work with, we did with Eric. And what it shows that essentially in this closed loop model, if, look in this case, for example. So this ripple, does it trigger upstate or not? On the other hand, upstate already started somewhere. On the other hand, it's clearly impacting some shape of upstate and probably make it starting a bit earlier. If ripple happens near down to up transition, it's actually in those cases, it's extend upstate. So it's a bit unclear. Do we have more ripples at the end of upstate just because they trigger downstate? No, does the ripple trigger downstate, or ripples happening near end of upstate can extend it but still get into the region of downstate? Again, I'm not going to discuss it more. It's still something I would like to explore more. But last few slides. So we did this modern work, and then it turned out that Rajat had in the Bruce McNaughton lab actually had data which we can use to try to test model predictions. So again, as I showed, this was in vivo recordings from mice in virtual environment. It was trained on two different environments, which was, one was trained a lot, it was called familiar context A, and another environment is a sort of new one, which is novel. And okay, we'll keep details, but basically what was done in those experiments, you can get template, reactivation template for each of those from rectilinear cortex for each of those environments. And then you can use those templates to see what is actually played and when during upstates. So this is, if you look at the middle plot first, this is when we only look at the middle third of upstate. And this is template matching results. This is time and again upstate going on from left to right. And if you have better match to familiar template, it's shown with red. Basically how well is match is showed and how high is this red dot. Red is familiar and blue is new. So you can see during middle of upstate, we see almost exclusive reactivation of the familiar environment. And during initial and later phase of upstate, we have a lot, especially during down to up transition, reactivation of the new environment as shown here in the blue. So if we, again, sum up this result in some sort of bars, this is the amount of reactivation happening in the beginning of upstate, middle of upstate, and last phase of upstate. And you can see that we have a lot of reactivation of familiar one everywhere, but particularly during middle phase of upstate, and very little reactivation of the new one during middle phase and significant during early and later phase. One thing to mention, we didn't have access to ripple data here, so some of the substates may have no ripples at all, and then they would replay familiar environment, so essentially all the red bars would be kind of pushed up. If we kind of present model in the same way, we get in, almost exact match. So we again see lots of reactivation of familiar environment everywhere, and specifically during middle phase of upstate, and much more significant reactivation of new one in the beginning and end of upstate, and very little at the end. Very little in the middle. So this is my last slide. Essentially what we propose is that slow wave sleep very naturally create, it's solving problem of interference by creating this interleaved kind of reactivation of old and new memories within each upstate. So those are essentially three cases which we can see, assuming that the ripple is arriving. So we can have reactivation of new one in the beginning and then old one in the middle. We have reactivation of both, a new one at the beginning and the end, again, old one in the middle, and we have reactivation first a familiar one and then new one. And this is actually based on empirical data, so this is percentages of how often we see each case in vivo recordings. So again, hippocampal ripples arriving near down to up transition or up to down transition, they can trigger new replay. And that's what we see in those, again, all these blue cases. So middle phase it cannot be triggered by ripple. New memory activation cannot be triggered by ripple. So it's always reactivate old memory. So again, this strategy kind of allows to form new memories without interference with old one, without erasing old one. Again, all this work, most of the work, new work I showed was done by Ryan Golden in our lab and Rajat Sahen in Chris McNaughton lab, and collaborators and other people contributing to the work. Thank you.
Okay, well, we seem to be having a ripple episode here. I hope everybody's ripples are rippling right now through your cortex so you can remember all the wonderful slides. So any questions for Maxim?
I have a question.
Go ahead, Mark.
So thanks, Maxim, for the talk. So just brainstorming a little bit between what you told us and what Yuri told us, I'm sort of wondering if there's the possibility of doing ripple intervention experiments in which you might simultaneously attempt to enhance one memory while getting interference on others. So meaning like you're not just interfering or enhancing, but you're trying to manipulate the relative strength of memories. What do you think about these kind of experiments? Would they be feasible?
I guess some of them have been done, right? Including in Yuri's lab, and that's probably the best way to test it. In our case, prediction would be, well, if you can detect kind of timing of the ripple, prediction would be if you delete or inactivate ripples which tends to arrive in the middle of upstate, then it's essentially not going to affect anything about new memory consolidation. If you specifically somehow interfere with ripple arriving near down to up or up to down transition, then where new memory consolidation when we would be kind of affected. That's sort of most immediate prediction.
Yeah, so I agree with that line of thought. I think there might also be additional predictions. So you had that plot of the two PCs, and you were showing us that to preserve the two memories, right, you need to have sort of the right amount of reinforcement, right? And so I'm wondering also if you could think about not just the timing of the intervention, but the relative number of interventions, whether you might be able to get interference or not. So
I think in that sense, probably more interesting experiment would be if you have access to three memories. Kind of two memories and new one would be, let's say, more familiar to one of those. So if you start to kind of interfere with ripples, again, depending on well, in experiments, always, in the model, we know for sure which ripple represent each memory and so on. So I think the problem in vivo, we can look at the reactivation and link it to which memory we kind of dealing with first or second. But when we look at the ripple, it's hard to say what memory it's supposed to reactivate. In fact, in those experiments, we cannot exclude that some ripples may still be representing old memories because consolidation is not fully completed, so it's much more complex situation. But Okay, I like to think about all the possible experiments, and even better if somebody can actually do them, but that's...
Thanks.
So, Mark, this, the idea was kind of done. It was Antonio Fernandez Ruiz and his group, and they showed that if you get rid of the ripples on one phase of the ultra-slow oscillation, then it's the recent memory, and if it's the other phase, then it's the older memory.
It was mainly about down to up, as far as I remember, right? They never looked up to down. Maybe I'm wrong.
That's true. It's not a complete experiment, but the gist of it was pretty much the same. But this is a time scale of a minute. So we are talking about separation of old and new with 30 seconds. How do you relate this to your model?
By minutes, sorry, you mean minutes versus 30 seconds?
So what they showed is that this is a slow, ultra-slow oscillation. It's about 1 minute. If they erase the ripples in this phase, the early part, then the old memory is stable, but the new memory is gone. So they showed, and the other phase, they also showed that what is the replay of the memory that was learned the day before or in the same day. So what I'm saying is that they show a separation in several tens of seconds. Your separation is hundreds of milliseconds. Do you see a good way of connecting the two?
Well, what we're trying to, again, point is, I guess it's slightly different framework. What we're trying to say is if our old memory, new memory represented by ripple tries to talk to area of the cortex where already pre-existing some old memory, so some synaptic resources are taken by that old memory. The question is how to protect that old memory, because it can be sort of erased. So in that sense, the only thing we're proposing is that the system design in such a way that even if we reactivate new memory in the beginning kind of or end phase of upstate, there is a part of upstate which will only kind of dealing and reactivating old memory, and that's very naturally create sort of protection, going back to all these ideas about interleaved training and so on being kind of a way to avoid interference. So that's why I think I actually like the time scale is fast, because in many cases interleaved training dealing with kind of slow time scale, you use bench of old data, bench of new data, for example, in machine learning and so on. What we are saying that each upstate of slow waves is actually designed to have kind of very fast reactivation of old and new memories, which is in a sense, again, maybe ideal situation, because we don't need to add any other timescales to the system to separate old and new. Of course, there are some other, like what hippocampus replaces, recent work about related to neuroregulatory tone and so on. There are lots of other timescales going on. But in very minimal case, it can be done within each upstate. That's kind of claim we are doing.
In mathematics teaching, they have a concept called interleaving, where, for example, you'll learn perimeter, then you'll learn how to calculate area, and so forth. So you're learning different patterns. Is this just so far removed from humans that it wouldn't have any application, or is someone actually? It seems to me that what you're doing is quite related to the concept of interleaving at a sort of a different level in education.
Probably asking somebody from psychology kind of field would be better way to ask the question. But in general, idea of interleaving different pieces of memory to learn is old. I mean, it goes decades back, and it has been sort of resurrected a lot again in machine learning, because that's the best way right now to avoid interference when you use some old data to mix with new one. And it's probably related, again, we are talking about slightly different situation. We are talking about what happened during sleep. But in principle, if you want to, well, I guess my totally hand-waving answer would be yes, but don't push me in details to say why.
But wait, just there is a difference that Barbara was talking about interleaving during awake.
Yes, yeah.
And you're talking about interleaving during sleep. But, and so they could well have different temporal scales, but they could be the same principle.
But principle is the same, yeah, because if you keep learning, training one thing, potentially you can damage more and more whatever was really kind of involved in same group of neurons, but related to another experience, memory, whatever you want to call it.
Thank you so much for the talk. I apologize if this was answered during your talk, or this is like too obvious to necessarily expand on. But I was wondering what you think about the mechanistic explanation of why the ripples during the up to down or down to up transitions would have the effect that you showed in the synaptic weight plots, in the sense of, you know, why, for example, 1/2 is or the upper triangular part of that matrix is modulated. For example, I mean, something that might come to mind is that during those transition periods, you have differences, you have differentials that could potentially be propagated to the weights, whereas if you're only in upstate, that might not be the case.
No, that's a great question. In fact, this is what we are working with Ryan right now to try to address. So some ideas that those transition kind of periods, down to up to down, kind of like phase transition the system. And the system is more unstable. Like you look at some measures like high Lyapunov value. You can sort of, okay, not going into details, but you can get correlation metrics, you can get some Lyapunov exponents and look at highest one, and it kind of shows, in a sense, stability versus instability of the system. So we believe when it's in the middle, I mean, okay, so when the middle phase of upstate, it's those values are low, so it's much more stable. It's much harder to move the system by external input to do something which is not trained before. During this phase transition kind of periods, down to up to down, system is much more sensitive and much more likely can be involved in a new pattern. Again, this is something, again, Brian can say better, but that's what we are trying to understand. I mean, not that maybe less mathematical explanation could be that during middle of upstate. Again, network already engaged in reactivating its own kind of, reactivating whatever connectivity patterns are trained before and represent, whatever memory traces. Probably there are multiple memory traces, and they could be reactivated in chunks, not the whole thing. In fact, that's what we also showed, because, again, this kind of, there are possibly multiple overlapping old memories. And beginning and end would be ideal situation. I better understand why beginning, less understand why end, but we're trying to figure out why network is more sensitive and more likely to be engaged in new pattern.
Thank you.
Okay, let's thank Maxim again.